In this video, we're going to talk about absolute extrema. So in the last video, we talked about relative extrema, which are the peaks and valleys in a graph, where they have to be in a open interval. So essentially in a neighborhood, like there has to be values before that and there has to be values after that. And you're talking about the smallest or biggest value, just like in a localized open interval of values. Now what we're going to talk about are what are the absolute extrema, the biggest and the smallest value on any defined interval. It could be the whole function, like the entire negative infinity to infinity if it's defined on the whole all real numbers. Or it could be maybe we're just looking at a portion of the function. Maybe we're going to then build into just looking at on a closed interval of a portion of a function. So now when you talk about the absolute min and the absolute max, the biggest and the smallest value on an entire interval, potentially on the whole function. And so as you start to look at that, notice that we no longer have this condition in the definition where it has to be an open interval of values kind of surrounding that. So endpoints now are going to have the potential to be absolute extrema, even though they're not local extrema. So that's going to be kind of a key difference here. So first, let's just take a look at some graphs here. So suppose in this first example, I was considering this function, which maybe is like the function, I don't know, maybe like 1 over x squared or something. So maybe there's a horizontal asymptote on the x-axis, and maybe the y-axis is also a vertical now asymptote. And, you know, we have this function that if it is like the graph, let's say of 1 over x squared, that is getting closer and closer to these asymptotes as we kind of go along here. So if we were to think about, well, what is the, considering the whole function, the absolute maximum, so the biggest value on the whole function, well, this keeps getting bigger and bigger and bigger here, and really same thing on the other side as well. So, you know, this does not have a biggest value. I can't say, oh, you know, 100 is the biggest value or anything like that. It keeps getting larger and larger and larger. So there is no absolute maximum. Additionally, there's actually no absolute minimum either, because these functions, but both branches, as we go further and further off to the right, these values keep getting smaller and smaller. Now, while it's true that they're never going to drop below 0, or they never even get to 0, they do keep getting smaller and smaller. Like if I said 1/10, you could say, oh, we'll just go a little further over and you're at 100th, or then go a little further over and you're at 1000th. So these values keep getting smaller and smaller and smaller. So in this first example, we have a situation where there are no absolute extrema of any kind, no absolute min, no absolute max, if we focused on the entire function. The whole function where it's defined, of course, it's not defined at 0, but so there would be none. All right, so now suppose we look at this next graph. Probably like a degree 4 polynomial would be my guess, right? Looks pretty typical of a degree 4 polynomial. Let's throw some arrows indicating for extra specificity. It keeps going up and out on the ends. Now, if I said to you, what is the biggest value on the whole function, you would say, well, same situation as last time. On the ends, we keep getting bigger and bigger and bigger. If I'm looking at the whole function, this is never going to have a biggest value. So we would make the observation that there are no absolute, or there is no absolute maximum. However, there is a smallest value on the function. So on this example, it happens to be at a location of a relative minimum, but that is the smallest value on this entire function. So this is the absolute minimum. So we do have an absolute minimum there. All right, so now suppose we kind of move away from looking at like the whole function or looking at you know, those two examples. Let's take and look at just a closed interval of a portion of a function. So let's take a look at number 3. So now if I was to look at this example, I have a situation where it looks like I have a smallest value right here. So it looks like that right there is going to be my absolute minimum. So it looks like I have a smallest value. Looks like that minimum's -1. It occurs at 1, but the actual minimum value is at, can't write there, can I? Minimum, that was supposed to be an M. So it looks like the minimum was at -1. And then it also looks like there is an absolute maximum. There is a largest value, and it's right here at this 4 is the maximum. It also happens to be the X location. So this is our absolute maximum. So it's looking like an absolute maximum is occurring at that endpoint, which is allowed. It's not any longer a part of the definition for absolute extrema that we have this open interval of values. An absolute maximum or minimum can occur at an endpoint. All right, so same kind of thing happened over here. It looks like we have a biggest value right here at, again, 4 is the maximum. So it looks like we have another absolute maximum here at 4. 4 is the absolute maximum. It occurs at x equals 1, but the max is 4. And that would have also been the location of a relative maximum, by the way. It would have come from where f prime didn't exist, it looks like, but that is a peak in the graph on an open interval there. And it's also the absolute maximum. And then it looks like we have an absolute minimum. The smallest value is right here at 0. All right, so what I want us to observe from these last 2 examples is when you have a continuous function on a closed interval, which we do in 3 and 4, we are guaranteed the existence of a biggest value and a smallest value. So we are guaranteed the existence of these absolute extrema. So this is what we call the extreme value theorem. So if you have continuity on a closed interval, you're guaranteed an absolute min and an absolute max. Now, where did these extrema occur? Kind of take a look back up at those graphs. They occurred at 2 locations. They occurred at either the location of the endpoints. So notice on those 2 examples that the endpoints were a couple of the absolute max in number 3 and the absolute min in number 4. Or the absolute extrema occurred at locations that were relative extrema. So in the middle of the function, those relative extrema that occur at locations where the derivative maybe is equal to 0, like the absolute min in number 3 was where f prime was equal to 0, or maybe where f prime didn't exist. So the absolute max in number 4 occurred at a location where f prime did not exist. So these are the possibilities of where absolute extrema can occur.